recording. Hi guys, and welcome to, I lost track of the weeks. I think we're in week 4. We're really getting into the heavy stuff now. We're getting into materials that are they're going to lay the foundation for a lot of things that we'll be doing. We'll be introducing, first of all, Kepler's laws this week, and they're extremely important, okay? And we're going to see something which is really how science works, okay? I know some of you probably are not planning to be doing science, but at least you will have really how the scientific method really works. The scientific method was invented, I would say, around the 15th century, just before Newton and all of these scientists basically started working on these things. It was invented actually by somebody by the name of Al-Hazen. He was living in modern day Egypt and actually also Iraq and all of those areas. And later on, his method, especially the emphasis on the hypothesis and how to formulate ideas and how to test them, and you can basically come up with an observation, then make a hypothesis, and that hypothesis has to have in it a testing. Basically, it has to be testable, and then based on that, you're going to check if the hypothesis holds, or maybe you need to revise it, and if it does, then what kind of conclusions you're going to build on it, and that's how science progresses. So later on, it was adopted by, among other people, Newton and other people later on in the scientific field. And now it started really by his observations in astronomy and also in optics. And later on, it went on other areas. Before it was formulated, though, astronomy went through these stages without basically formulations. This is one of the big takeaways from this class in how scientists think. Because if somebody comes up with a story to tell you, here is what we know, or what I think is happening, at least with the stars and the planets and the moons and so on and so forth, he or she has to back it up with a whole approach, basically with observations and all of this ideas and how they come together. Because anybody can tell a story. Anybody can make up a story. And if it's not scientific, it's just another story, fantasy, that's all, okay? So you will see this at work. To give you an idea about these 2 units, basically 11 and 12, people in the old days, when you look at the sky, and we talked about that when we were talking about the how the idea basically of the fact that the sun is not revolving around the Earth, because the discovery that the size of the sun must be bigger than the Earth, but that was confronted immediately by a problem, because he needed to know the parallax. That's something that we can experience on a daily basis, but that could not have been observed, so that idea was rejected. Just so the point in here is we had a model that the Earth is in the center of the universe, and everything else among others, the sun, the moon, the planets, and the stars, they revolve around it. So the Earth is the center of the universe. Because you go outside and look at it, and that's exactly what you see. Okay? That's what you see day in, day out. And then there was some discrepancies in the observations, some problems, that led, among other people, Copernicus later on to say, wait a minute, this behavior is indicative of the fact that the Earth is not the center, at least, of the solar system. The Earth goes around the sun. And that is a model that emerges later on to explain the motion of the planets around the sun. Basically, that they are moving around the sun. There was another idea also that people believed in, based on philosophy, actually, is that all these paths must be spherical or circular, at least if you're looking at a two-dimensional object. Because, again, the circle is an ideal object, and that's the most symmetrical object, and symmetry in here, unless there is an external force, symmetry must govern. So that's the reason behind it. But then later on, Mr. Copernicus also fell in the same trap, that he thought that this path must be circular. It took further observation by another astronomer, actually, and those people, they did not have telescopes at that time. They were just using their eyes, basically looking at this object and documenting their position, especially Tycho Brahe. He collected a huge amount of the observations, a lot of it, okay? And those observations, he kept track of all of these planets, whether Venus, whether it's Mercury, whether it's Mars, whether it's the moon, whether the positions of the sun day in, day out over a long, long period of time. And he needed somebody to come and help him with the math. He was not a math inclined person, so he wanted to have somebody help him, and he brought on board Mr. Kepler. Mr. Kepler, when looking at those data and those observations, he immediately rejected the idea that the paths were circular. They are not circular. They are a little bit kind of circular, but not exactly circular. We call that an ellipse. So they're elliptical in paths. So that's the first law. He then said that basically that all the planets, they go around the sun in elliptical paths, where the sun sits in one of the focal points. Obviously, we need to understand what the focal point is, and what the ellipse is, and what is meant by the semi-major axis and the semi-minor axis, and those properties of the ellipse. So this is geometry now. He went a step further. He actually, when looking at those data again that Mr. Tycho Brahe collected over that span of time, and he was doing the analysis, he noted the following. He said that as the planet moves around the sun, when it's close to the sun, because the ellipse has properties, as I was saying, sometimes the sun, because the sun sits in one of the focal points, so sometimes the planet is close from the sun, and sometimes it's further away. When it's close, it speeds up, and then when it's further away, it slows down. Just like what happened when you're playing with a rubber ducky in the bathtub. If you put it close from the sink, it's actually going to spin faster. But if you move it away from it and let the water basically go into the sink, it's going to spin slower. So that is the behavior. As a matter of fact, he came up with the quantitative number. He says the ratio, if you can imagine a line linking the sun to the planet, and that line is going to go around basically tracking the planet. That line sweeps equal areas at equal times. So those two laws. So the first one, that the paths are not circular or anything else, they're elliptical. The second thing is that this line, this imaginary line, sweeps equal areas with equal amounts of time. The third law that he came up with, and that took him a little bit of time. He didn't come up with it immediately. He said that the time it takes for the planet to go once around the star, once around the sun. For example, for the case of the Earth, it's a year, 1 year. For Venus, it's less than a year, slightly less than a year. For Mars, it's almost 2 years. So for Jupiter, it's almost 12 years. So that's the time. If you square that number, and you take the average distance between the star, the sun in this case, and the planet, and you cube it, the ratio of these two numbers is constant. So again, he had a lot of data to work with, and he came up with the third law. So these are the three laws of Kepler. So again, now we went from this model, where the Earth was the center of the solar system, to where the sun is the center of the solar system. Data now gave us these three laws. That's not enough. We needed an explanation. So it took the work of Mr. Newton to come up with a theory to explain all of that. Mr. Newton compared the motion of the moon around the Earth to the motion of an apple when it drops toward the Earth. If you take an apple and you let go of it, as a matter of fact, any object and you let go of it, it's going to fall due to the force of gravity. He theorized that what causes the moon to go around the Earth is the same force that causes the apple to fall on the Earth. The only reason why the moon is not falling on the Earth is because it's moving fast enough. As it's falling, it's catching itself. That's all, basically. So now he has this comparison between the two, and he came up with what is later on called the universal law of gravity. Now, why is it law of gravity? First of all, it's the same thing that causes the apple to fall, but he postulated that this gravity is not just causing the apple to fall on the earth or the moon to go around the earth, but it's the same thing that holds the earth to go around the sun, or Jupiter or Mercury or all of the other planets to go around the sun. That's the word universal. You can even push it further and say that this law is the one that governs the motion of all of the stars in the galaxy, in all of the galaxies, in the local group, and all of the groups in the cluster, and all of the clusters in the universe. So it's really a universal law of gravity. So he formulated that theory, and he was able to explain the three laws of Kepler by doing so. Obviously, we were talking about one of the main things that you're going to take from this class and how scientists think. And this is the idea of how to progress. But, and this is a critical, important, basically objection. If all you do in science is to explain just what was absorbed, that's not good enough. If all you do is explain what has been seen already, what has been measured already, that is not good enough. A theory in science must go beyond that. It must make predictions. So if Mr. Newton, all he did was to explain the three laws of Kepler, that is actually no big deal, because anybody can explain anything that happened with just enough faith. You can come up with any kind of explanation. So why should we believe in Newton? Because he made predictions, or at least a theory made predictions. When Halley's comet, at that time it was not Halley's comet, it was a comet basically that came in, Mr. Halley computed based on Newton's laws now, that explained the three Kepler's laws, and he predicted in 76 years and some odd days, this same object will appear again. Long after he passed away, long after Newton passed away, sure enough, that comet reappeared again. So later on, it was named Halley's Comet. So you see here, a theory was able to explain observations, laws of Kepler, which are based on observation of Tycho Brahe, but that's not good. It needed to go beyond, make predictions. And actually, it's not just that. There are other predictions that you can use with Newton's laws. And I'm just pushing this idea a little bit so that you understand the context of where these two units are headed, so that you have an idea of what's going on. Obviously, there was a problem also with the Newton's laws. It worked beautifully for Venus. It worked beautifully for Earth. It worked beautifully for Mars. It worked beautifully for Jupiter. It worked beautifully. Those are the only objects that were known. It works beautifully also for the moon, and it worked also beautifully for the 4 moons that Mr. Galileo has observed revolving around Jupiter. So it gave immaculate results. There was one thing I didn't mention in here. Mercury. It had an error in it. It did not work. No matter how much you try and make corrections, see if maybe your observations need to be refined or your calculations are maybe need to be refined, there was a discrepancy, and that discrepancy basically is the one that led Mr. Einstein to revise the whole thing and come up with a better theory. That explains Kepler's laws, that explains everything that Mr. Newton has explained and goes beyond, explain Kepler. The motion of Mercury. So, and again, if all Mr. Einstein did was just to explain what Mr. Kepler has done, what Mr. Newton has done, and basically explain only the thing that was observed for Mercury, that is not good enough. Also, so Mr. Einstein would not really have any credit whatsoever. It needed to go a step beyond. And that's exactly what Mr. Einstein did too. He made predictions. One of them is the gravitational lensing that was observed about 10 years later. He made other predictions also. One of the predictions that Mr. Einstein didn't like at all is black holes. He said, although the calculations lead to the existence of black holes, he thought that these are too monstrous to be accepted. Later on, they were observed. So in other words, this is the whole point in here of if you take anything from this entire class, is how scientists think and how science progresses using these ideas based on observations and making predictions and so on and so forth. Okay. Sounds exciting? No? Okay, very good. Thank you. Okay, so let me share with you at least an overview of what we know today, okay, in terms of a planet before I delve into the PowerPoints, okay? I have in here a software for those of you who have Steam, basically the gaming thing that people use it for gaming. I have a software called Universe Sandbox, which is really a nice simulation software for everything, whether the planets in the solar system or exoplanets or also galaxies and things like that. So let me share with you, share. I have it in here paused. You see in here in the bottom, it's paused. And I think the date is sometime in 2017. I don't know why I went so far. It doesn't matter. The whole point in here is just to have an overview of the solar system. If I move if I pan throughout the software in here, you see all of these planets and you can see the names in here. You see Saturn on this side, Mercury on this side, the sun is in here, Mars is a little bit above, Venus is in here, Earth is here, Jupiter is here. And right now I am about 5 astronomical units away from the sun, which means I can see Jupiter, but if I zoom out, I probably will include more planets. Like you see the blue path in here, that is actually the path of Neptune, okay? Before that, there is probably also Saturn in here that I included. I can even see Pluto in here. So I'm actually in a path right now. So you have Uranus in here, and that is Neptune. So I'm about probably 30 astronomical units or 40 maybe astronomical units from the sun. Okay, I'm very far away from the sun. But the point being in here, look at this plane. If I cut it this way, all of the planets are more or less on this plane. This is what we call the ecliptic plane. And it's very critical to see this distinction. Why in the world the solar system formed in such, ignoring this tiny object. And you see Haumea in here. I see Makemake in here, Quaoar in here, and some other objects in here, even Pluto for that matter, and all of this other, basically what is known as TNOs, trans-Neptunian objects. These are objects past Neptune. Remember, the planets are Mercury, that we know today, okay? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Those are the planets. 4 of them are big gas giants, and 4 of them are small, basically rocky planets, or basically they are not gas. They are made out of rocks, basically, and silicate. The point being in here, these are the big objects. With the sun, they sit on the same plane. Other objects, the tiny objects in here, they must have formed probably, they're too tiny for them to be ejected probably by Jupiter and all of the other objects. So the solar system, when it formed, when it came to be, it has formed on the same plane. We're going to talk about that because we need to explain this thing. We need to come up with an explanation of why the solar system formed this way. So this is now, I'm looking at it from the top, and I'm looking past the path of past the orbit of Neptune, which is the furthest object. So right now I'm looking at Neptune and Uranus in here, and even Saturn looks very close from the sun at this distance. Saturn, which is about almost 10 astronomical units, is very far away compared to 30 astronomical units for Neptune, or Uranus, which is about 19 point something astronomical units. So these are distances that are unimaginable. And what's an astronomical unit? Again, we saw that it's this distance from the Earth to the sun. So Neptune is about 30 times further away from the sun as the Earth is. Even Jupiter looks very close from the sun right now at this distance. Obviously, Pluto in here, sometimes it gets closer to the sun than Neptune, and most of the time it's not. Most of the time it's far away. It's almost 40 astronomical units when it's far away. And Let me get closer in here to see the inner solar system, the ones that we talk about. So here is the first object. This is what the ancients saw. Mercury was one of the objects that either comes, this is from the night side of Mercury, this is from the day side of Mercury. It looks similar to the moon, actually, when you see it, because it's heavily cratered. This has a lot of impact from when the solar system formed. There was a lot of impact immediately there. It's one of the properties of Mercury, if I can get this one in here, if I go to the motion, it tells me how far Mercury is from the sun. It's at its closest approach is 0.3. At its furthest approach is furthest point, it's about 0.4. So it's average is about 0.387. What is 0.387? That means it's 38% closer to the sun than the Earth is, because 1 AU is the distance to the sun. So it's very close from the sun. So this is the first object that ancients have seen move around. It does not stay in the same constellation. And like the regular stars, doesn't matter, take any star, Rigel, Betelgeuse, anything you like, they sit in their constellation, meaning the group of stars move together from season to season, or depending on the sky, if there's circumpolar, they move around the Polaris. So they're together, the entire shape stays together. This one is not. This one usually is either just before the sun during the sunrise, or just after the sun during sunset. And Mercury is a big planet, actually. You see with the naked eye. It looks super bright early in the evening, or late in the early in the evening, or just after around sunrise. Okay. The same thing is true actually for the next one, which is, if I can find it in here, I'm trying to zoom out in here to find it, just to give you an idea of how big these sizes are. Okay. Which is Venus. So let me zoom in on it. And again, Venus, we're looking at it from the night side. And again, even from the day side, you don't see anything. It has a super thick atmosphere. You cannot see it. I mean, you have to have really radar technology to penetrate that super thick atmosphere to see its surface. Again, the size of Venus is almost that of the Earth. The features under the surface, I mean, this is extremely hot planet right now because of this greenhouse, because of this tremendous atmosphere that it has, that is mainly carbon dioxide, and it has sulfuric acid in the atmosphere, and it's really extremely hot. If you can stand on its surface, and you can't, you can see the sun because of the haze that is over all the planet in there. Okay, so again, this is Venus. Obviously, the next, and I'm going to show it just to give you an idea of how amazing it is. I mean, it's really a pressure thing in here, which is the Earth. Okay, this is the Earth. We're looking at the daytime of the Earth right now, and this is the evening time in here. So I think I took a time which is 5:43 p.m. on this date. I don't know, which is March 3rd, so of this year, 2017. So obviously, if I let go of the time, you're going to see all of this thing starts moving, and I really don't want that because I want to see this object up close. Again, it has a lot of water on its surface. It has so many geological features that we're going to study further because it really serves as a sample or an example for us to understand what's going on with these planets. The third object, or the fourth object from the sun, is actually going to be, of course, you know, it's Mars. And Mars is actually, again, it has a lot of features on its surface. It has a very thin atmosphere. That's why you could, and like Venus, you can actually see its features. Okay, with a good enough telescope, you can see a lot of the features on the planet. It's kind of a reddish planet because of the presence of iron, basically, in its crust. But it's also a rocky planet. I'm just going to go slightly, actually a little bit faster with the next planets because we still have a lot of ideas to talk about in this unit. And I just want to bring your attention to this object between Jupiter and Mars. And these objects include Vesta, and include mainly, I'm looking for it, And here, the Sedna, for example, it looks very close from here, but believe me, it's further than even the thing that you can imagine. As a matter of fact, I'm going to click on Sedna to just give you an idea. Sedna, in its closest approach, it's about 76 astronomical units from the sun. So it's very far than even Pluto, twice as much as Pluto can be, almost 2 times. Versus when it's further away, you're looking at almost 900 astronomical units. So we're kind of lucky at this point to see it because it's close by. The reason why it's looking close by is because I'm looking at the side. But if I'm looking at an angle. But if I change the angle, I mean, it cannot even see it. It's going to go away completely. It's way past even Uranus. So for right now, I'm focusing only on the objects in here. So I have Vesta in here, but before Vesta, there is another object that is important in this region, which is, I'm looking for it and I cannot find it. And that is Ceres here. This is one of the big dwarf planets that exist between Mars and Jupiter, okay? And actually its distance is about, distance from the sun is about almost 3 astronomical units. I mean, 2 something astronomical units. It's further than Mars, but closer than Jupiter, which brings me to, and there are a bunch of them, by the way, part of the asteroid belt in here. That is actually something that we are going to discuss more down the road. And again, we have Jupiter in here. Jupiter is about 5 astronomical units. And then, and it's the biggest planet in the solar system by far. And it weighs more than all of the other planets combined, including Saturn, which is the next one in size. And then you have, those are the planets that we could see in the old days. So all of these planets, as I was describing earlier, they change location from constellation to constellation to constellation. So the name planet itself really is description of this behavior. They were called planets, which really means wandering stars, stars that wander from location to location to location. And like the normal stars, which are stationary, these stars, which we thought that they were stars, sitting on the same celestial sphere, are actually moving around. They don't stick around. If you keep track, for example, of Mars, you will see it in this constellation. A week later, it starts to shift. If you wait 2 months, 3 months later, you're going to find it in a completely different constellation. The same thing is true for all of the other objects. So these are called planets, which really translates to wandering stars, stars that move around. Obviously, at that time, we didn't know about Uranus. It was discovered by Herschel with his telescope. And then later on, we 2 mathematicians basically independently, using Newton's laws, they made a prediction for the another planet past Uranus, because the path of Uranus was just enough disturbed so that there is another object that disturbs the existence, and that is how Neptune was discovered. Because based on calculations, they said, okay, go and look in this region of the sky, you're going to find it, and sure enough, it was discovered. Notice the shape of this, the color of these 2 planets. One of them is like a greenish, bluish color, and the other one is actually bluer than the other one. That's because of the methane that is in their atmosphere. So that is basically how these 2 planets are. Past that, when Pluto was discovered, we thought that, okay, this is the 9th planet. Then later on came out far more than that. I mean, far more than that, actually. Quaoar, Sedna, Makemake, Haumea, and a bunch of other dwarf planets that later on, and that's where the classification of dwarf came in. This is basically, if I look very far away from the solar system, the whole thing that I can see is just the sun, really, and there are some objects that are far away. Now we think there is even another planet that is big enough to be counted as a planet, and that is planet 9, and the hunt for it is going on for the same reason why Neptune was discovered, namely that the path of those tiny objects past Neptune, they are disturbed enough so that there is a 9th planet that the hunt for it is going on, but it must be very far away from the sun, extremely far at this point, that it's in the hundreds of astronomical units, that it is very difficult to find with even the best telescopes that you have in here. And because of its distance, it's very far even to pinpoint its location. So the hunt for it is ongoing right now, although there is a new speculation that Planet 9 may not exist after all, and there is probably a different mechanism for why those dwarf planets are actually have their paths a little bit distorted. So this is what we know today. This is what we know as of today, basically as of the solar system. And we know it not just because of telescopes, extremely powerful telescopes, which are useful for tracking these objects, and a lot of these objects were there. We were able actually to send manned mission to some of these objects outside of the Earth, namely the moon. We were also able to send landers and actually orbiters and probes. So we were able to send objects to the different planets all the way to Pluto and past Pluto, and also to the sun. So we have advanced enough in technology now to have not just basically based on observation, but actually based on measurements, and those measurements came up with data into the structure, into the periods, into the times for them to revolve around their own axis, into the atmospheric conditions on those objects, and into the different, in some cases, even the sampling of the soil and things like that. So that's where we stand today, and we came a long way up to this point. So let me share with you the PowerPoints from the units. Let me find it. Okay. So we have 2 units this week. And the first unit, unit 11, describe the patterns of motion in the sky that planets exhibit. Okay. And I basically briefly discussed that. Contrast the geocentric and heliocentric models. A geocentric model puts the Earth at the center of the solar system. A heliocentric model puts the sun at the center of the solar system. Okay. Why? There is something that we're going to talk about in here, which is the retrograde motion of different objects. If you are driving on the freeway, for example, at 63 miles per hour, and somebody comes in and zooming past you at 67 miles per hour, there is a relative motion. That person is coming from behind and going to overtake you. And if you're looking, if you are sitting in that car, it seems like you're moving backward, although you are moving forward. Both of you are moving in the same direction. And if you're passing somebody going at 60 miles per hour, you're going to overtake them. And if you look at the person, if you're not really paying attention to the fact that you're actually moving, and if you look at the car, it looks like it's drifting past behind you in the opposite direction. So in the relative motion of objects around one another in the sky, there is that apparent motion backward and forward, okay, depending on which one is overtaking which. For the case of Mars, the Mars appears, and that's really what the exaggerated behavior was noticed first, is that Mars appears to be moving like everybody else in the same direction, but at some points it starts to move backward, takes a long time moving backward, and then continue moving forward. So we needed an explanation for that. So in the geocentric model, we had to explain that. Because how in the world the Earth is sitting in the center, and if everything is moving in a circle around the Earth, like for example on the celestial sphere, including the sun and the moon and all of the other objects, how come Mars all of a sudden decides to move backward? What causes it to do so? So we needed to come up with an explanation. Now, for the heliocentric model, we also need to explain that. So we come up with a model, which is, okay, the sun is in the center of the Earth, the solar system. The Earth and Mars are moving in that direction. But one of them is moving faster than the other and is overtaking the other. That's why we see the retrograde motion for Mars. Obviously, the retrograde motion is not just for Mars, for all of the objects in the solar system, because we are moving and they are. So we're going to observe it for Venus, and we did. For Mercury, and it does. Ceres, all of the other objects in the solar system that I mentioned before, Jupiter and Saturn, they do that. Although the most exaggerated one that we can see all the time is that of Mars, because Mars is far away from the sun. It is not like the Venus, for example, which is closer to us at times. Venus is very close from the sun, and sometimes it gets, I mean, we can see that as exaggerated, for example, for the case of Mars, because Mars is far enough so that when we are overtaking it, it appears moving backward. So we need to explain that based on the two models. You make an observation, and you come up with a model to explain those observations. The model, if all it does, it explains those observations, it's no good. It needs to go a step beyond that. So which one makes predictions for the next retrograde, and which one will make predictions for another retrograde? That is actually the more accurate model. That's the one that is good. The other one that cannot, basically all it does is explain things, is no good. So that's one of the reasons why the heliocentric model won at the end, and the sun is actually in the center of the solar system, not the Earth is. Okay. And then define terms associated with the planetary positions such as opposition, conjunction, and greatest elongation. For those sitting in 125, I know some of you are, you will have a complete lab on this thing in here. But the point being is this, and it's part of your lecture anyway, so you're accountable for it too, is that part of the geometry actually of the planetary geometry is that depending, because here is the sun in the middle, here is the Earth on one side. A planet can be behind the Earth or in front of the Earth next to the sun. So when it's behind the Earth, it's in opposition. What's in front of it, it's in conjunction. And there are two possibilities for the conjunction. For the case of, there are only two planets, so you can do that. That's Mercury and Venus. So if Mercury sits or Venus sits between the Earth and the sun, this is an inferior conjunction. But if they are in the opposite direction, that is actually a superior or superior conjunction. If they are on the opposition, like for the case of Mars, they're immediately behind us. So basically, we form a line with the sun. So Sun, Earth, and Mars. And then there are two other locations in this case, and that is the greatest elongation. Because here is the thing: doesn't matter which object you're looking at, especially the inner objects. That's probably a good example to look at. Here is the sun somewhere in the middle. They're spinning around the sun, and we are too. But at some point, they're spinning faster. The inner objects move faster. Remember the second law of Kepler that I mentioned? Yes. Or actually, the third law, I'm sorry. The third law says the closer they are, in this case, the faster they move. The rubber ducky is a example. So at some point, they're going to move away, but then they start to come back, and then move away and come back. That angle, that is what is known as the greatest elongation, because they move away, but then they start to spin around the sun and come back again. So those two locations would define the greatest elongation. I'm just giving an overview of this unit in here. And then explain how Copernicus estimated the distance of the planets from the sun. So this is basically what I said before. This is up to Mr. Copernicus, because before Mr. Copernicus, the idea was that the planets revolve around the Earth, including the sun, by the way. Okay. So again, we explained this one here. This is in the geocentric model. The geocentric model puts all of the objects in a big sphere, and they're moving around the Earth. So the Earth is not doing anything, basically. As the sun passes by immediately above us, that is day. And as the sun goes in the opposite side, it's night, and so on and so forth. So that's how the objects move around the Earth. And there is good reason for why this is true, probably, is because if you go outside and look at the sun, come an hour later, it has shifted by 15 degrees from its current location. That is true. I mean, who can argue with that? The sun in the morning was in the east. Around noon, it's just above my head. Later in the evening, it's on the west. And then the moon comes up, and same thing. So that's what prompted the geocentric model. But again, the geocentric model had a problem to explain. One of them is this so-called retrograde motion of Mars. I want you to look at the date. First of all, this from February 10th, 2016 to September 8th, 2016. It's almost a year, okay? Well, planet Mars is moving versus the background constellations. Case in point, in here you have Antares, which is this is a big constellation. So if you focus on this constellation, you will see that Mars moves around, and then at some point moves back. The minute it starts from here, hear me? I don't know if you guys can hear me or not. Sorry about the issue. Can you still hear me or not? Okay, very good. Thank you, Kiara. Anyway, the point being, I don't know, I got disrupted. I don't know when this voice and probably even audio went out. But we were talking about the, let me share the screen again. The retrograde motion, and that it goes back. Basically, an object will be in retrograde when it starts from this point and moves forward. Okay, and it moves against the constellation. The same thing was actually observed for Saturn and all of the other planets. So we needed to explain that. Okay, in the model where the planets move around the Earth, basically this is the geocentric model. So basically, in this case, the interpretation is that these objects go in spherical orbits. Okay, you have the moon, which must go closer because it moves faster, and then the objects in here, Mercury, Venus, and so on and so forth, all of the other objects. And these paths, as I was arguing earlier, must be spherical paths. That's the argument that was made for them. So they go in spheres around the Earth. But then you needed to explain the retrograde motion. So for the retrograde motion to be explained, so they came up with an explanation that this object, especially planet Mars, for example, actually goes in a circle, a tiny circle around the big circle. So as it's moving away in that big circle, at some points, if you follow the planets from here to here, it's actually in retrograde motion. And then it's going to go forward, and then it's going to go retrograde, then forward, then retrograde, and so on and so forth. So that explains, in a sense, the retrograde motion. Depending on how long it takes, the radius of this smaller circle must be big enough just to make that retrograde to happen, whether it's fewer or more. So that is the point being in here for this retrograde motion and how it happens. Okay, so that was explanation for that. One of the questions that you need to ask yourself, is this a real retrograde or is just an apparent retrograde? And the answer to this one, this is actually a real retrograde. This is a real motion in a sense that the planet is at times moving in this direction and at some other times moving backward. If it is real, you need to tell me why the planet decides to slow down and move back and then move forward. What causes it to do so? What force causes it to do so? That is really the key in this case. If we can find a force that does that, maybe you're right. But if there is no force that causes that, then there should not be any reason for it to do this behavior. So that was the explanation, at least for the retrograde motion the planets. Now, let me tell you about Mr. Copernicus and why he was entrusted with this whole thing. Because his whole model was based on Ptolemy, which was published in the almost 2,000 years now, more than 1,500 before Mr. Copernicus. And based on those calculations, the positions of the sun and the planets and so on and so forth, it made predictions when the next holidays are going to happen, when, for example, Christmas is going to happen, when, for example, Easter is going to happen, whatever, all of this religious events for the church, it needed those things. But then, if you look at the calendar, it starts to go off compared to what the actual time of the year is. For example, Christmas, instead of happening in the winter, started happening in the spring. So the church had a real problem and they needed to solve it. So they asked Mr. Copernicus to look at this calendar and try to fix it. That's all. That's his task. He was tasked to fix the calendar so that all of the events now happen in the same time when they're supposed to be. Okay. Well, as I was saying, he rejected this idea that the sun is actually, that the Earth is in the center of the solar system. So when he did that, the calculation started to make more sense to him. The only thing that he made a mistake with, he stuck with the circular paths because he couldn't find any reason why they shouldn't. Now, if he does that, then the planet, like the Earth, is moving faster because it's closer to the sun than Mars. The Martian year takes almost 2 years as much as we are. In other words, the Earth does 2 rotations around the sun when Mars does barely 1. So at some point, when we are on Earth looking at Mars, the projection in the night sky is here versus the background stars and constellations. When a week later or 10 days later, or whatever you're counting, the Earth moves and so does Mars, but Mars moves slower. The arc it covers is less than the arc the Earth covers. So the projection, in this case, it's still moving forward. In other words, it shows that Mars is still moving forward. But later on, the Earth moves a bigger arc in the same time of that we decided. If it's 10 days, for example, after 10 days, the Earth moves this much arc, whereas Mars will move, but a smaller arc because it's moving slower. So if you look at it, then Mars appears to have moved back versus the constellations. And if you take another 10 days later, Mars again moves slower than the Earth, which covers a bigger arc, and you look at it and it looks like Mars went completely backward. Until you come to some point in there, then again, remember the elongation that I was talking about? Then at some point when we reach the elongation, at least around it, that the planet starts to move forward again. So this is the heliocentric model. For Mars, it does not need something special, extraordinary for it to move backward. There is no external force that causes it to move backward. It's moving in the same direction, and so is Earth. The only difference is one of them is moving faster than the other, and that is Kepler's law, the third law, actually. Okay, if you time how long the Earth to go around one arc distance, and another arc distance, and another arc distance, and do the same thing, basically the angle cover it, and do the same thing. And if you can estimate the distance to the Earth and the distance to the sun from the distance to the Earth and distance to Mars from the sun, you will find that the square of that time it takes for the Earth to cover the entire period and the entire orbit, and the square of the time for Mars to cover its entire orbit, if you divide the ratio, it's the same ratio as the cube of the distance to the sun from the Earth and the ratio of the cube to the sun from Mars. So it's a constant, doesn't change. Okay, it's fixed. So that is why one of them, because this distance is further, so it must be moving slower. Just like the example of the rubber ducky, if you put it closer from the sink, it moves faster than if you move it further away. And basically, you have to have the top full, and then you have to open it so that the water can spin inward. And then the rubber ducky, when it's further away, moves slower. So that is really the analogy that works in this case. And it has to do later on, as I was explaining in the beginning, that Mr. Newton came up with an explanation, and the explanation has to do with something called the conservation of angular momentum. And we're going to come back to this. So Mr. Newton came up with a number, which is called the angular momentum. And that angular momentum, if there are no external forces, to be more specific, no external torques, there is no reason for it to change. And that's really what governs this. That's really what dictates this. Okay. And that is the same reason why you also have the rubber ducky behave the way it does, because as long as you don't push it, if you just leave it the way it is, the water will spin faster near the sink than when it's further away, and it drags with it the rubber ducky. Again, this is some of the stuff that has to do with the geometry. Okay. As I was explaining earlier, you have the conjunction, and you have the conjunction of the inner planets. You have the inferior, which is very close, and you have the superior, which is in the opposite direction. And this line in here is the line that defines the this is basically the Copernicus model now, since he put the sun at the center of the solar system. And the opposition on this side, and you have the quadrature in here. And I was talking about earlier, for example, if you take one of these planets, it doesn't matter. Let's say, for example, this yellow one. So at some point, it's going to give me this. This is the further away, because at some point it's moving in, let's say, for example, eastern direction or whatever direction you pick. And then at some point starts to move back toward the sun, and then later on move again towards us, and so on and so forth. So those are the different geometries that were used. And for those, again, sitting in the 125, we're going to have an extended calculations in here. We're going to make predictions on when the next retrograde happens based on current data, based on known data. So you can use this model actually to make calculations. Okay. So the opposition is when Earth lies directly between the sun and the planet. So it's just basically, I hope that it's self-explanatory near the geometry. Okay. So the Earth is in here between the sun and the planet. So this is called the opposition. Okay. So all of this is just the explanation of this model in here. Again, Mercury and Venus, because they're closer to the sun, they really usually don't further away from the sun because of the fact that they are very close from. They orbit the sun actually, and as the sun is moving in the sky, they're actually moving with it. For case of Mercury, there is that angle of 28 degrees, basically at most between it and the sun. For the case of Venus, because it's further away, the angle can be very far away, as much as 47 degrees. But at some point, they're going to go closer, okay? And that is the greatest elongation. So the greatest elongation in this case is 28 degrees. But at some point, remember, Mercury can be on the other side of the sun. So the elongation in this case is going to be 0. So it's going to be moving around the sun. For our perspective, it looks like it's crossing in and out of the sun. So when it's further away, that is the greatest elongation, but then it comes back and then stays in this orbit as the sun moves, and it's dragging with it those two objects. As a matter of fact, it's dragging everything, including the Earth, by the way. The sun is drifting in the galaxy, and it's taking with it everything that is attached to it gravitationally, including all of the other objects I described earlier in the universe sandbox. Okay. And this is actually something that Mr. Copernicus was able to make calculations based on his model, based on all of this geometry I was describing. He found that the distance to Mercury, based on his model, is about 0.38. Now we know this average is about 0.39. So it was not too far. Okay, he made an extreme good calculation. His model is very, very good. He also came up with a value for the distance to the Venus from the sun of 0.72, which is exactly what we knew today is. I mean, probably it's a percentage error, but it's really this is the Earth. This is the standard, basically. This is the distance is 1 for the Earth. Remember, an astronomical unit is 150 million kilometers or 93 million miles. So that's what we were calling an astronomical unit. So For the case of these two planets, it's less. Take 93 million and multiply it by 0.38, you're going to find about 30 million miles for the case of Mercury. For the case of Venus, it's going to be about 65 million miles. So it's still far. So but this is basically the number. For the case of Mars, also, it's right on the money. It's 1.52. Okay. Here, when it starts to differ, for example, for the case of Jupiter, it's still acceptable. 5.22 versus 5.2. That is actually an acceptable value for also Mercury. But by far, Saturn now we're starting to get off. The error starts to be big. Okay. Because as you go far away from the sun, his measurements actually, because the angles at that time, you really need to have far more precise measurement tools than what he had available at hand. But it's still good. From 9 astronomical units that you found, 9.2 to 9.5, that is actually a very good number too. Okay, so this is unit 11. Again, I made the introduction also to how unit 12 is going to go. Unit 12 is going to take us from what we know, basically based on Mr. Copernicus. So Mr. Copernicus came up with what is known as a revolution, because from the idea that the sun, the Earth is the center of the universe, which probably, any person, I myself, included anybody, if you ask him, and if you didn't know anything about this, all of these objects are moving in the sky above us. But it took his insight into those observations to say, wait a minute, those measurements for the greatest elongation for the case of Mars, for the case of for the case of Venus, for the case of Mercury, gave him that motion around the sun, and then later on the motion around the Earth, gave all of everything fits in place. The whole picture really came in place. So that's why it's called the Copernican revolution, because he changed the whole game. He was tasked to fix the calendar, but he fixed our perspective of things. Okay. I'm gonna stop right now here. And do you guys have any questions about the homework? Because there are 2 homework assignments this week, and also we have homework from last week. Of course, we still have unit 12 to cover Thursday. How are you guys doing with the homework? Yes. Finding it easy? I know a lot of you are not in here, so here is what I was going to say about that issue, because I really wanted to bring that to your attention so that you guys are also aware of it. Okay. There is first of all, I am on campus, okay? In a few minutes, actually, I'm going to leave so that you guys, if you want to meet, we can meet there. Because I have actually another lab that is starting this week with section 1. This is not, some of you probably have, maybe some of you are sitting in 1, I don't know. But I know some of you are sitting in section 2, actually, which meets on Thursday. We can meet on campus, okay? I know my office is still not ready. I know that they're still working on it. But there is the STEM center that we can always meet in it, or you can actually go by yourself to the STEM center. And that's really the point that I'm trying to make in here. Please take advantage of that resource. It's a very important resource so that you can take advantage of it. Okay. So do not really struggle with that. Reach out to me about the homework. Okay. I know it's great, is encapsulated with other stuff, but you really have to also take care of that, because as I said before, doing the homework is what will enable you really, in addition to doing the reading and doing the discussions and doing the quizzes and all of that. But the homework, I find it's one of the most powerful ways of understanding the content, because if you do it, and that's why I go through it in detail at times, if you do it, you really are going to really empower yourself in understanding a lot better what's going on, and you will feel far more in control of these things. I know one of them is due this week, so that's why I'm emphasizing about it. Sounds good, everybody? Okay, very good. Thank you, guys. Okay. So I'm going, like I said, to stop at Unit 11 because I really want to give you time so that you can go and read Unit 12. Thank you. And also make sure that you do your homework, and I will be here around. So if you guys have any questions, please don't forget to ask. Okay. Thank you, Susan. Thank you, everybody else. Thank you, Alex, Chiara, and everybody else too. Okay, I'm going to stop the recording, and I'll see you guys. Bye.